Hello, everybody. It's my pleasure to introduce you what we are doing in the IRIS project at EMIRI. What is EMIRI? EMIRI is the Energy Materials Industrial Research Initiative, and we are developing the value chain energy materials. Where is the slide? So we are developing the energy materials value chain within the IRIS project. And here specifically today, we take one example being the battery materials. And I will try to show you that developing safe and sustainable batteries is still an equation with several unknowns. How will we do this? First, by mapping you the full value chain of energy materials. Next, taking one example, meaning the battery value chain. I will try to illustrate you the design actions that we are taking battery related, some design principles, and it is mostly focused on improving materials efficiency, but there are trade-offs to be made between efficiency improvement and SSbD. Next, we will discuss briefly safety by design, concluding with what Lee already introduced, a life cycle thinking approach, and some conclusions. So what is the value chain of energy materials? It is a very broad range of technologies, and we have published those technologies in the EMIRI roadmap, technology roadmap, already in 2019. We have covered the full scope there of energy technologies with a specific focus on advanced materials, because we believe that advanced materials make indeed a difference in these technologies. So what are these technologies? It's first about solar, new solar generation and harvesting technologies, including also wind power in the energy harvesting and production technologies. Second, specific focus on batteries, battery materials, as well for mobility as for stationary. Thirdly, we have looked at all the technologies related to hydrogen, hydrogen for mobility, and that means fuel cells, that means hydrogen storage materials, distribution of hydrogen. Fourth sector that we considered is the chemical energy storage and CCU, CCS, and there obviously it's the electrolyzers. It is capture, CO2 capture and utilization, and it is with that CO2 and hydrogen, the production of synthetic fuels. And finally, the fifth category is about energy efficiency. That is also a wide range of different technologies, including building efficiency improvement, new glazing technologies, new insulation materials, new lighting technologies, etc. So this is the full scope of the energy value chain. And please, if you want details on what the technologies are, what the R&I needs are in each of these technologies, look at the EMIRI roadmap published in 2019. So if we then take the example of battery materials, it starts at the mining, at the winning of the different raw materials in a sustainable way. Next, we need to produce the advanced materials, as well for the cathodes, for the anodes, for the separators, for everything. Again, in a sustainable way. Then we need to process them, these advanced materials, coat them, coating processes on the electrodes. Finally, and bringing that all together in a cell manufacturing line. followed by module manufacturing, and coming finally to a pack assembly structure. That pack goes into different applications, portable batteries, if we talk about small packs, mobility applications and stationary applications. And when we come to the end-of-life phase, there are different options. The packs can be recycled. Processes exist based on pyrometallurgical recycling, hydrometallurgical recycling, and a new process in development, direct recycling. But there is an alternative, and the alternative is using those packs again in second life, after refurbishment, after remanufacturing, etc. And we will come back to that later. So if you look at the diagram over the different segments in that value chain, and you will see that with yellow asterisks, I hope, we have quite a good position in Europe in each of those segments. So we have actors, players into the raw material mining and production. We have established players in the manufacturing of active materials, as well for cathode materials, for anode materials, for the electrolyte, for the separator, for everything. So we are quite well positioned in Europe for that. We have cell manufacturing, we have pack manufacturing, and we are strong in the application. Look at all the OEMs now involved with electric mobility. So we have a strong position in the applications, not only for automotive, but also in stationary and a little bit in portable applications. So coming to end of life, we have several players and good players in the recycling. They are looking at expansion. There is a huge need for expanding recycling of batteries in Europe and in the world. And we have some initial activities already on second life. So what is the battery industry doing? What are we doing in research for design actions? And we will consider 4 levels. First at molecular level, molecular design level. Next at product design, process design, and end of life. At molecular design level, it's all about minimizing critical raw materials. What are those critical raw materials? Obviously, the lithium, the cobalt, but also natural graphite, coming still for 80–85%, I believe, from China. Securing access of those raw materials from sources outside of Europe. And roughly 90% of our raw materials are imported, and only about 10% are produced locally in Europe. So we need to sustainably search for new mining industry in Europe. And that many initiatives and many projects are about that, trying to find the right and raw materials in Europe. And there are examples. For instance, in Finland, there are reserves in cobalt, in nickel. Work is done, just as an example, on lithium in Spain and in Portugal. So expanding the existence and discovery of raw materials in Europe. But at the same time, secure access to secondary raw materials through recycling in a circular economy context. And based on those virgin raw materials and recycled raw materials, build the advanced materials for the next generation of batteries. That's what is done at molecular design level. On product design, there are in fact 2 strategies. There is a design to performance strategy, and there is a design to cost strategy. In the design to performance strategy, we continuously try to improve the properties, the performances of the materials, incremental, but also disruptive. Incremental by constantly improving for lithium-ion the energy densities, for instance, and disruptive by developing solid-state batteries. Always in the context of R&I linked with the industrial ecosystem. The design to cost is about meeting people's expectation for lower cost and developing lower cost technologies in lithium-ion. And that can be done with LFP, lithium iron phosphate. That can be done with LFMP, adding manganese into the composition of LFP, or that can be done with, for instance, HLM. HLM is high lithium, rich manganese cathode material. We try also to have access to those products as close as possible to the manufacturing plants and to the consumers in order to avoid sticks and in fact, being as close as possible to the sources where they need to be. We develop plurifunctional applications, try to standardize all the applications for safety. We try to integrate design to recycling and design to sustainability into the materials, but there are gaps. And the gaps, obviously, here is, I forgot the gaps for the previous one. For the molecular level, it's all about availability of raw materials in Europe for sure. Here it is about having sufficient renewable energy, not only for the production of the materials, but also for the application. And in the context of massive rollout of electric mobility, considering the impact on the electricity grid in the application, and always meet customers' expectations for safety, for cost, etc., and for sustainability. On process design level, many things happen. Efficient manufacturing processes are required with the lowest CO2 print possible. And that can be a competitive edge of Europe compared to Asia, compared with China, for instance. We are developing that. Also, new processes are developed at materials level, production level. For instance, cathode active materials based on recycled precursor materials. Development of new and much more efficient calcination processes, because that is one of the energy requiring steps into the production of CAM material. So new calcination processes are more efficient. At cell manufacturing level, a lot of work is done on aqueous processing instead of a solvent-based NMP processing. So NMP-free processing, water-based processing. Dry coating is developed, and that is applying the powder directly on the collector and hammering, in fact, mechanically adhering the powder to the collector. A lot of work is done on infrared and laser drying furnaces, more efficient. And finally, an important energy-consuming step in the cell production is the formation of the cells. So development of more efficient cell formation processes is also done. At pack level, there is a new technology. As you know, cell-to-pack technology, and that is, in fact, more and more applied already in Europe. No use of modules anymore, and use of large cylindrical or prismatic cells directly into the chassis of the car configuration. At process design level, what are the gaps identified? Reduction of scraps rate. In an efficient gig of manufacturing production line, we still talk about roughly 10% of scraps. So reduction of scraps is aimed for, and there is an absolute need for more training and education and for more skilled people, and there is a lot of attention paid to that. End-of-life design, it's all about circular ecosystem development and building the stakeholders and streams, optimal streams in end-of-life design. There are several options. The most obvious option is recycling, but it's more than that. At end of life, we are considering remanufacturing. That means a reuse in the same application. So rework the batteries and reuse them, for instance, in mobility, after a first life in mobility. Refurbishment is to another application. So using end-of-life batteries in stationary after refurbishment and giving them second life. What are the gaps identified here? We need disassembly of those large packs, 500 kilogram packs, 600 kilograms packs. So we need more automation in the disassembly of the packs. We need methods for recycling of low value content batteries. Remember LFP, remember HLM, lower value, more difficult recycling from the economic point of view. And there is a lack of business models still for second life to be further developed. And here, and Christina is here, we have an excellent example that we, combining in fact end of life with second life, we have developed a new process in the context of Battery 2030 Plus. And it's all about, in fact, at each stage of the end of life, considering the option of second life. And that starts at pack level. After collecting all the information of the pack, and the battery passport will be very useful for that in the future, after collecting sensor information, etc., decide on pack level whether to reuse it in second life, in containerized grid systems storage, for instance, or going a step downwards to modules. And always based on a very fast and accurate state of health determination. Again, at module level, measure state of health, decide whether it is still useful for second life, do it then, for instance, in home storage applications, or going to recycling. The same question at cell level, opening the cell smartly, and now direct recycling comes here as a new invention, not recovering the powder and not melting the powder like is done in pyrometallurgy, not leaching the powder as in hydrometallurgy, but in fact reconditioning that powder. So separating the graphite powder from the cathode material and doing a reconditioning on the powder. For instance, re-lithiation, for instance, reconfiguration of the crystallographic structure, particle size distribution, etc. So reconditioning of the active powders and reusing them directly in new cell fabrication. That can be applied, such technology, to any battery technology. And that's what we are developing together in Battery 2030 Plus. Coming then to some design principles, and I'll just take one example. That is materials efficiency. The battery world is constantly working on making better battery materials, better cell performances, energy densities, volumetric, gravimetric, power density, circularity, number of cycles, cost, name it, we are working on that. Everything is quantified in KPIs. Those KPIs have already been given in 2016, I believe, in the set plan. And that has given effect life to the development of many new battery generations, from 1 to 5. We are currently in generation 3, lithium-ion always, and that means in generation 3, improving the capacity, high capacity direction, or high voltage direction, higher voltages. That's where we are now, and soon, within maybe 1 year, or we already start with it, is solid electrolyte batteries, solid state batteries. Many different configurations are possible, but solid state batteries will come soon. And that brings us to generation 5, beyond lithium-ion, and that will not be for tomorrow, honestly. Lithium-ion will stay the technology of choice for still many years to go. But there are, in all that thing, trade-offs to be made. And especially looking at generation 5, it's all about the substitution of critical raw materials. Lithium replaced by sodium, lithium replaced by calcium, by magnesium, etc. Bivalent materials. We try to do that, but it's still at the cost of performance. When we try to replace or substitute the binder, PVDF, that is still at the cost of performance. So that's what I try to illustrate you with some more examples. We try to constantly improve the properties of the batteries, but it's not always easy from an SSbD point of view. And we need further LCA and LCCA studies to prove the real contribution to sustainability with the new systems. Just 3 examples. There's a lot of work done now on the replacement of lithium-ion by sodium-ion. China started with it. We already have several startups in Europe based on sodium-ion. The materials are known for the cathode that can be layered transition metal oxides, that can be Prussian blue, Prussian white. The anode material is also known, hard carbon, for instance. Yeah, clear lithium can be replaced by sodium, much more available raw material, but we are not there yet with the performances. Sodium-ion still, roughly, only has half of the energy density of lithium-ion. Further work has to be done on improving those energy performances. The recyclability will also be quite difficult for sodium-ion because there is less value to be grabbed. And maybe for the toxicity, that also will need further clarification with the risk of hydrogen cyanide in the case of the choice of Prussian blues and Prussian whites. So still work to be done. Fundamental work on further development and improving the system. Second example, LFP. Remember, design to cost direction. There is a contender now for LFP, HLM, high lithiated manganese-rich cathode material, offering indeed the potential of better performance than LFP. By the way, phosphorus is also a critical raw material. So improving performance with HLM, improving recyclability. It will be easier to recycle HLM than LFP. But all those data need to be confirmed by further LCA and LCCA assessment. Third example, lithium sulfur. The cathode is sulfur, so no cobalt, no nickel, no critical raw materials. Ideal from a point of view of sustainability, of SSbD, but again at the cost of performance, at the cost of energy density, and especially here at the cost of durability and cycle life. On safety by design, LCA, SLCA, it's obvious. Safety is considered as a very important issue and is considered in all the battery research initiatives, in Battery 2030 Plus, in Batteries Europe, in the Battery Partnership. So safety is transversal area in system development. Standardization, several standardization bodies work on the needed standards for safety procedures. Substances used in manufacturing or present in batteries are regulated under the provisions of REACH, and there are many European regulations. The battery directive is under revision. There is eco-design directive, there is a REACH regulation. There are many documents that can be that are regulating safety. But our impression is that those tools and methodologies performing environmental and especially social life assessment need further development, and that from an holistic perspective. And that methods like design for recycling, design for sustainability, these are a little bit slogans. They need to be further developed at an early stage from the beginning in materials and in product manufacturing. This is an easy case for me. Leah came already with the example. This is a very, very nice and good article published in 23 on battery materials, battery innovation landscape. It gives you a little bit everything about sustainability criteria, aspirations, and I really recommend you to read this article. You have the link here. It gives you a very good perspective about SSbD in batteries. That brings me to some conclusions. On sustainability, we are doing a lot. We try to reduce continuously the critical raw materials content, and that in a context of massive rollout of the application, massive rollout of EVs. The same for energy storage. We try to constantly improve the manufacturing processes to make them more energy sustainable, working with the lowest CO2 print possible, based on sustainable sourcing of raw materials. We have attention to water, energy, chemicals, and waste issues in the manufacturing processes. We try to, and we have the means with the recycling processes that exist and are further in development to secure access to secondary raw materials. And there are a lot of efforts done on improving skills and improving the workforce. On safety, there is lots of attention on the reduction of hazardous materials. Safety is seen from the whole chain, whole value chain perspective. And as I mentioned to you before, unfortunately, there are still questions, there are still trade-offs to be made between what we try to do, making the best battery, and SSbD practices. And that brings me to the end, and I thank you for your attention.